how to calculate bending moment, shear force and axial force in a beam. The beam AD as shown in this figure is supported at A and D, and it carries an inclined load of 10 kN at C. How do you think the load at C is transmitted to support A and support D? Of course, the external load has to be somehow transferred to the beam section and eventually reach at A and D with an appropriate shears depending on the position of the load. We call those appropriate shears of the load at the supports are the reactions. So this will be dy and the reactions ay. From the applied external load to the supports, the beam has to transfer the load internally, and they are called internal loads, and they are bending moment, shear force and axial forces. Before calculating the internal loads, we need to find out the reactions. So let's calculate the reactions first. And before calculating the reactions, or to calculate the reactions, we need to make a free body diagram. This is the free body diagram of the given load. We have the inclined load of 10 kN, which we resolve in x direction, so which is 10 times cos 45, and in y direction it becomes 10 times sine 45, which is cy. And at beam support we have vertical reaction and horizontal reaction, and at roller support D we have vertical reaction dy. Now we need to use equilibrium equations. So using equilibrium equations in two dimensions, so summation of force in x direction equals 0 gives us cx plus ax equals, because cx and ax both are pointing rightward, and from the sign convention this is positive, which equals plus 7.071 plus ax equals 0. So we get ax equals negative 7.071, which indicates ax is opposite to that we assumed for the unknown support force in the free body diagram. The free body diagram shows ax as to right, so ax must be left because we got the negative sign. This indicates that the axial force at A is in tension, that is away from the beam. Now use next equilibrium equation, that is summation of moment about A equals 0, and use the normal sign convention. For this equation, ax times 0 plus ay times 0, because ax and ay both are passing through point A, so distance is 0, minus cy times 8 plus dy times 10, which will give us, this gives us dy equals 5.657 kilonewton. In this case, the positive value indicates direction of dy is same as was assumed in the free body diagram. The free body diagram shows dy is positive, so dy must be upward. Now use the third equation of equilibrium to solve ay, which is summation of fy equals 0. The equation is ay upward positive minus cy downward negative plus dy upward positive equals 0. Substituting the value, we get ay minus 7.071 kilonewton plus dy equals 0. So substitute dy equals 5.657, which eventually gives ay equals 1.414 kilonewton. Now let's try to find out the internal loads. To see what are the internal loads and how the inclined applied load at C has been transmitted to support A and support D, let's cut the beam at, let's say, 3 meter from support A. So if we cut the beam will collapse. So beam will collapse like this and like this. So this indicates that there must be some forces in the beam at this point to resist collapse and keep the beam in equilibrium. So if we apply the correct internal actions, which are shear, moment and axial force, to the cut face, the free body diagram should be held in equilibrium again, and we can use the equations of equilibrium to work out the internal actions at the cut. So once we cut the beam and make a free body diagram, so let's say the left hand side of the beam, and make the free body diagram of this side of the beam. This side of the beam should look like this. Two reactions are at their position, and we cut the beam at point, let's say this is point B. Then we have vertical shear force at B, horizontal normal force at B, and the rotation at B. So there are 3 internal loads at point B, so that this portion of the beam will be in equilibrium. We should be able to get the same free body diagram, similar free body diagram for the right hand side section of the beam as well, but the analysis will usually be easiest if you choose the free body diagram with the fewest load. So in this case, free body diagram AB is easier, because if we see the right hand side, you have support reaction and vertical load, external load at C, and horizontal external load at C. But if you see the left hand side, only the reactions are the load. So the left hand side is easier in this case. These unknown forces and moment, unknown forces BB and NB and the moment MB, are in fact the shear force, axial force and the bending moment at point B. So to calculate these forces and the bending moment, we can use equilibrium equation. As usual, we assume this sign convention. So rightward force in Fx positive, upward force in y direction positive, and anti-clockwise moment positive. So now let's use summation of force in x direction equals 0, which will give minus ax, which is opposite to the normal positive sign. So this is my 7.071 ax plus nb equals 0. We should get nb equals 7.071 kilonewton. So the axial force at point B of the beam is 7.071 kilonewton. Now let's apply summation of force in y direction equals 0. This will give us this 0 equals vertical upward AY positive minus the VB is going down, so VB should be equal to 0. Substituting the value of AY equals 1.414 kilonewton, we get VB equals 1.414 kilonewton, and this is also positive. The positive value indicates the actual direction of shear force is the same as we have assumed. And the last equilibrium equation is summation of moment at B equals 0. So here we have MB, which is acting anti-clockwise, so positive, and VB is passing through point B and NB is passing through point B, so they will have only 0 distance from point B, so we can neglect that one. AX is also passing through point B, so the only remaining load is AY, which is 1.414 kilonewton times the distance is 3 meter, and this is trying to rotate the beam in this direction, which is clockwise direction, so negative should be equal to 0. This gives moment at B equals 4.242
kilonewton meter and positive.